Yesterday I asked you what a baseball team that was 42-8, 42 wins, 8 losses, had in common with a train that was rolling down the track. And you told me that they both have momentum. That means they're both hard to stop. They're both difficult to stop. Now, the one we want to focus on, of course, is this one. The one that has real momentum, physical momentum, as opposed to the psychological momentum. What gave this train momentum? What made it hard to stop? There were two things. What was one of them? Good, velocity. The faster it's moving, the harder it is to stop. And we know that intuitively, right? Anything, not just a train, but the faster anything's moving, the harder it is to stop. What's the other thing that made it hard to stop, that gave it lots of momentum? Good, mass. The heavier something is, the faster something's moving, the more momentum it has, the more difficult it is to stop. Now, sometimes an object's momentum is due almost entirely to mass. It's not moving very fast, but it's got a lot of mass, so it's still got a lot of momentum. Sometimes it's due almost entirely to velocity and hardly anything due to mass. And then sometimes it's due to a combination of both the mass and velocity, but both are required. We also defined a term yesterday, inertia. What was the difference between momentum and inertia?
Momentum is for an object that velocity, everything has inertia.
Good, good. Inertia is essentially, we didn't define it exactly this way, but essentially how hard it is to change its motion. Okay. That means if it's moving, how hard it is to stop it or make it go faster. If it's at rest, how hard it is to get it moving. So it's similar to momentum, but it's not exactly the same thing, because in order to have momentum, it's got to be moving already. Inertia, it's got as long as it's got mass. Now, let's take a look at these two trains here. First one, does it have inertia? Yes, because it's heavy. It's moving. It's heavy. It has inertia. Does it have momentum? Yes, because it's heavy and it's moving. Does this one have inertia? Yes, because it's heavy. Doesn't matter if it's moving or not. Does it have momentum? No, it's got to be moving and be heavy in order to have momentum. We talked about momentum as being a vector quantity. What do we mean by that? Sorry? Yeah, it has a direction associated with it. In fact, it's always the same direction as the velocity is. So if the velocity is to the west, the momentum is to the west. If the velocity is 60 degrees north of east, like one of the questions you saw yesterday was, then the momentum will also be 60 degrees north of east. Finally, we gave you an equation for momentum. It looked like this. Lowercase p with a little half arrow over it. That means it's a vector. Comes down to the definition, really, right? The product of mass and velocity. What units did we have mass in? Kilograms, yep. What units did we have velocity in? Meters per second, good. And of course, this one would be kilograms times meters per second. There were a lot of times when we have to convert 2 kilograms from grams. You guys remember how to do that? This is like Science 9 stuff, isn't it? Or Math 9? Convert grams to kilograms? What's the conversion factor there? Yeah, it's 1,000. So what do? Do we multiply by 1,000 or divide by 1,000? Yeah, we divide by 1,000. And if you can't remember, do what I said yesterday. Guess. I mean, don't guess the number. Like, don't say, I'll divide by 967.2. No, like, you got to remember the number. But if you have to guess whether it's multiply or divide, then guess. Just check your guess. If I have 100 grams and I divide by 1,000, that gives me 0.1 kilograms. Well, that number seems to make sense. If I had 100 grams and I multiplied by 1,000, that's 100,000 kilograms. Doesn't make a lot of sense. So make a guess if you have to. Check your guess and see if it makes sense. Let's go kilometers per hour to meters per second. Who remembers the shortcut for that? Yep. Times it by 3.6. Okay. That's okay. It's okay. It's wrong, but it's okay. Let's check that guess, okay? I mean, I've made that mistake before too. And I probably will again, so it's okay. Just make sure you check your guess. Let's say we have 100 kilometers per hour. That's you know, a pretty moderate speed on Highway 2 to Edmonton, right? 100 kilometers per hour. Pretty low, in fact. That would be, if we multiplied it by 3.6, the equivalent of 360 meters per second. That's about 20 meters per second faster than the speed of sound. So, by going 10 kilometers per hour under the speed limit on the way to Edmonton, you'd actually create sonic booms. That's not realistic, right? So it wasn't multiplied by 3.6, it's divide. It's okay. So we make that mistake, it's okay. Just fix it. Just check your answer and fix it. So it's going to be divided by 3.6. 100 divided by 3.6 would be 27-ish. 27 meters per second, a quarter of a football field in 1 second, is a lot more realistic than 3.5 football fields in 1 second. So it is divide. Here's one for you. Didn't do this one with you yesterday. You don't see this very often, but I've seen it a couple of times. Kilometers per second. I mean, something's got to be moving really, really fast to be moving kilometers per second, right? A meteor or something like that, maybe, is moving kilometers per second. How do we convert that one to meters per second? No. You started off right, though. Say that again. Say exactly what you just said again, and I'll tell you when to stop. Stop. Multiply it by 1,000. That's it. All we have to do is multiply that by 1,000. You don't need to memorize that. Right? What's the conversion here? Seconds is already there. There's nothing to convert there. It's kilometers per second over meters per second. And meters per second. We just have to convert kilometers to meters. Kilometers to meters is multiplied by 1,000, right? So if you ever see, maybe you see a new one that we've never seen before, centimeters per second. Centimeters per second, just convert centimeters to meters. Okay, if you recognize that, it's not that hard to do. We good? All right. Yesterday we did this example in class, and I'm not going to go through the entire thing again. I just want to point out a couple of things and then give you a question to work on yourself here. We had to recognize when we saw this problem that there is an interval of time over which this problem occurs. Okay, there's this object, this 1.5 kilogram object is falling from a certain height down to the ground. That takes time. But we need to calculate the momentum not over that interval of time, but at one specific moment. And this question is phrased such that we're going to calculate the momentum at the end of the problem. So yesterday, if you remember, we said PF, the final momentum at the end of the problem, was equal to m times VF, the final velocity at the end of the problem. But we didn't have the final velocity. We had the mass. We didn't have the final velocity. Does anybody remember how we got the final velocity? Kevin? Good. Vf squared is equal to Vi squared plus 2AD. And then we turned around and we solved for Vf, right? Now, there was another way that none of you did yesterday, I don't think any of you did yesterday. We could have said EI is equal to EF, right? MGH, initial, is equal to 1/2 MVF, final. Would that have worked? Solve for VF? Is it any better than this way? No. In fact, in the end, it ends up being the same thing. They both give you the same answer if you do it either way. All right, so we solve for VF there, we plug it into here, and then we end up solving for the final momentum, and we get what we get. What I'd like you to do right now, please, is to try this question. It's multiple choice question number 1. You got your worksheet booklets yesterday. Halfway through that worksheet booklet starts a bunch of multiple choice questions. If you have a little bit of trouble seeing it on the board, then you can look at that booklet and see it a little bit closer up. All right, we'll give you a few minutes to work on that, and then we'll take a look at what you got. We'll take a look at this here now. Most of you got this correct, but we'll go through it real quickly anyways here. The big thing with this is to recognize that, again, we want to find the momentum at a very specific moment in time, and that is when the ball hits the ground. The other thing to notice is that we have a velocity here, but it's not the velocity we want. Okay, we know that we're going to do ultimately the same thing as we did in the last practice question that we did. Final momentum is equal to the mass times the final velocity. But v is not 20 meters per second. We have to find v using the same method as we did in the last question. The difference here is that vi is not 0. Vi is 20. So let's say vf is equal to the square root of vi squared plus 2ad. That's going to be the square root of 20 squared plus 2 times negative 9.81 times negative 5. Because it falls 5 meters, right? Its displacement is neg 5 meters. We get a final velocity there, a final speed there. We plug the velocity into here, and we would find that the momentum ends up being 2.9 kilograms meters per second down. Is that okay? For those of you who didn't get the correct answer, is that okay? Good. What I'd like you to do here right now is, for the next 10 minutes, please, is take a look at the questions on worksheet number 1. What you don't finish here in class will be homework, but I want to give you an opportunity to get a start on it at least so that you can ask me questions in class before you go home tonight if you're struggling with this at all, okay? So in 10 minutes we'll move on, but let's make some productive time of our next 10 minutes. All right, let's finish those questions up for homework tonight, and let's take a look at one more multiple choice question now, please. It's multiple choice question number 2. So take a look at your booklet, please, or just look up at the board, do question number 2, and then submit it on your phones the same way as you did question number 1, please. All right, guys, I want to take a look at this one now. The reason that we chose to do this question, the reason that I chose to do this with you in class at least, is partly because of the unit conversion here. We have to recognize that the cruising speed of this supertanker is in kilometers per hour. We may want to circle that in red or something just to draw attention to it, okay, that we have to convert it to meters per second. But also because I wanted to drive home the point of how to record certain numeric response questions, how to record it on a diploma exam. Okay, this morning, I had people choosing 5.55. The answer is 5.56, by the way. I had people choosing 5.55. I had people choosing 5.56. I had people choosing 5.5. I had 5.6. I had just 5. I had 5.56 times 10 to the negative 9, or 10 to the positive 9, whatever it was. All these different answers that told me that people knew exactly how to solve this problem, but just didn't know how to express it. Just didn't know how to put it into the, if this is a diploma exam, onto your bubble sheet. Okay. So that's what I want to focus on here. We multiply m times v in order to get the momentum. The mass, as you can see here, the mass is 1.00 times 10 to the 9. And the velocity ends up being, if we convert that to meters per second, which we have to do here, it ends up being 5.5555. Let's go to 4 or 5 decimal places before you round it. Then when we multiply those two numbers together, we end up getting 5.56 times 10 to the positive 9 kilograms meters per second. Now, look carefully at how they want us to answer this question. It says, the momentum of the supertanker at cruising speed expressed in scientific notation is b times 10 to the w. We're looking for the value of b. In other words, we don't want the exponent here. I don't care that the exponent is a 9. Okay, we don't need to put that in. In fact, if you do put it in, it's wrong. All we want is the value of b. The value of b, the base, is 5.56. So if this appears on a diploma exam, and this one did appear on a real diploma exam, and you put 5.6, you would have it marked wrong. If you put just 5, you would have it marked wrong. If you put 5.55, you would have it marked wrong. If you just put 556 without the decimal point, you would have it marked wrong. If you put 5.56 times 10 to the 9, you would have it marked wrong. All they want is the base, the 3-digit base with the decimal place in there, 5.56. Does that make sense? If you got that wrong, just because of format right now, don't worry about that at all, right? That's why we're going through this, is to teach you that. Okay, I can't expect you to be perfect at this before I teach it to you. By the end of the course, I want you to be perfect at it. But right now, that's part of the learning process. Question?
Like, is there a lot of inertia?
14. Yeah, 14. Okay, I want to take a look at, again, another momentum problem, but it's a slightly different kind of momentum problem. And then that's where we'll wrap it up for the day here. This one says, this is on page 452 of your textbook. An object has a constant momentum of 2.45 times 10 to the 2 kilograms meters per second. We want to find out what the momentum will be if the mass decreases to 1/3 of what it was, and its velocity, its speed, increases 4 times what it was. So we want to find out what the momentum is, what the momentum becomes. It was 2.45, right? What does it become after I make these changes to it? But this seems like kind of a tough question because we're making changes to the mass and the velocity without even knowing what the mass and the velocity were to begin with. How do you do this? How do you quadruple, multiply by a factor of 4, the speed or the velocity of this object when you don't know what to multiply by 4? When you don't know what it was. For a question like this, we have to use a technique that I call variable value changing. Normally, when we're solving a momentum problem, we will use the equation P is equal to m times v. We still will. If that's what we use to solve a normal momentum problem, then that's what we use to solve this problem. But it's kind of tough right now because we don't know what m is and we don't know what v is. I'm going to say my original value of momentum, PO, my original value of momentum, is m times v, but it's also equal to this value, 2.45 times 10 to the 2. This is what it starts out as, 2.45 times 10 to the 2 and m times v. So nothing new here. We're just writing down right now what appears on my data sheet, m times v, and what appears in the question itself, 2.45 times 10 to the 2. That's what my momentum is before I make any changes to it. Now let's make the changes. That's my original momentum. My new momentum, Pn, my new momentum, is also mass times velocity. But understand that when we write down an equation, the equation is only symbolic. The one that we write down, at least, is only symbolic of a real equation. There's no equation that's really m times v. The equation for momentum is not m times v. It's mass times velocity. We just represent mass by m and velocity by v. Well, momentum is still mass times velocity, but we're no longer going to represent the mass by m. The mass is now not m, it's 1/3 m. Right? It says it's decreased to 1/3 of its original value. So our new equation is not mv anymore. It's mass times velocity, but mass is 1/3 m. And velocity is not v. Velocity is 4v. Does that make sense? Right, we're not messing with the equation. We're not saying, oh, that equation mv is no longer valid. We're saying it never really was. We're saying that the equation is always mass times velocity. We just sometimes represent it, or usually represent it by mv. Well, this time we're representing it by 1/3 m and 4v. Now, let me ask you a quick question. Here's a good question for you math whizzes out there. What's 1 times 2 times 3? 6. Good. What's 2 times 1 times 3? 6. Good. What's 3 times 2 times 1? 6. Good. What's 3 times 1 times 2? 6. Good. Good. So what I'm saying here is that it doesn't matter what order you multiply things in, you get the same value, right? 1 times 2 times 3 is the same as 3 times 2 times 1. Well, if that's the case, then 1/3 times m times 4 times v is the same as saying 1/3 times 4 times mv. Agree? I can just multiply those numbers together in a slightly different order, and it means the same thing. Now, I'm going to simplify it a little bit further and combine the 1/3 and the 4. It becomes 4/3 mv. Still okay? Now, here's the crux of it. Here's the really important step. It's all important, but here's the really important step. The kicker. We know what the value of mv is. Look. mv, it says right here, mv equals 2.45 times 10 to the 2. So let's sub in 2.45 times 10 to the 2 to replace m times v. Because that's what it equals. How do we know that? Because that's what I wrote down, my very first step. Now let's calculate 4/3 times 2.45 times 10 to the 2. And let's see what we get. We get 327 kilograms meters per second. So we quadrupled a velocity. We cut the mass down by a factor of 2/3 to 1/3 of what it was. We didn't know what the velocity was or what the mass was, but we were still able to determine what the momentum becomes after we made those changes. When you see a question like this, don't just try brute force. Don't just try random things. You will not be successful. Okay, there are other ways to solve this, but in my opinion, the best way is the method that I just showed you. Step number 1, write down what you know. That's the equation and the value of what it was before you made changes. Step number 2, make your changes. Make your changes. Instead of m, it's a third m. Instead of v, it's 4v. Then tidy it up a little bit. And then finally in step 3, replace mv with whatever the value of mv is from step 1. And you've got your answer. Is that okay? Okay, there's a couple of these questions that I'd like you to work on as well. Your homework for tonight will be to finish that worksheet that you were working on a few minutes ago, worksheet number 1, if you haven't finished it already, and to do these 2 questions that appear on page 452. You have almost 15 minutes left in class, so you've got a good opportunity to get all or most of this done. One thing that I want to caution you on before you go home, though, the answer to number 1 says 9.28. It's wrong. I believe the correct answer was 3.09. You can check that when you start working on this. I believe it's 3.09. Take a look at the question for a second, and let me quickly explain to you why they got the wrong answer. The momentum, what does the momentum become if the speed of the bullet, if the mass of the bullet decreases by 3/4? What's the mass become? 3/4 m? It decreased by 3/4. What's the mass become? 1/4 m. So you're not going to use 3/4, you're going to use 1/4. It didn't decrease to 3/4, it decreased by that amount. So it becomes 1/4. Now, when they did their answer key, they used the value of 3/4, not 1/4. But that's wrong. So you guys make sure you use 1/4 and make sure you get that answer that's down there. Okay? You got the next 12 minutes or so to see what you can do with his homework questions, okay? Let's get at it.